Good morning everyone. This is Sirichandra from CSCF, roll number 24951A05BN. Today I am going to talk about first order non-homogeneous equation. Introduction to first order non-homogeneous equations. First order non-homogeneous equations are differential equations. These equations contain a homogeneous term which is a function of independent variable. Understanding these equations is crucial for applications in physics, engineering and other fields. Consider the first order non-homogeneous differential equation y dash plus p of x of y is equal to q of x, where we know how to solve it using the integrating factor. Now let's try another approach. Next is definition and form. The first order non-homogeneous equation involves first derivatives of the independent variable. The general form is represented as y dash plus p of x of y is equal to q of x. Here p of x is the coefficient of y and q of x represents the non-homogeneous part. Second order linear ODE non-homogeneous undetermined coefficients method. Let's explore the solution to non-homogeneous second order. A y double dash plus b y dash plus c y is equal to f of t. It is easier. These are the some of the examples for this form. From the above example, we see to guess the correct form of the equation is crucial. If we could not guess the form correctly, we could not find out one particular solution. Of course, most of time we may not guess correctly in the first try. In that case, we try another form again. Well, for the special type non-homogeneous ODE, we have the general results about the form of the solution. Thus, if we can remember them, it will definitely help us to get the solution quickly. Basically, we do not need to try again and again. Next is homogeneous versus non-homogeneous. Homogeneous equations have the form y of y dash plus p of x of y is equal to 0, where the q of x term without the q of x of term. Non-homogeneous equations include an additional function altering the solution behavior. Recognizing the difference is key to applying the appropriate solution techniques. Next is solutions overview. The general solution of a first order non-homogeneous equation consists of two parts. The first part is a complementary solution which solves the associated homogeneous equation. The second part is a particular solution that satisfies the non-homogeneous equation. Next is finding complementary solution. To find solve the homogeneous equation. This can be achieved using the method of separation of variables or integrating factors. The complementary solution represents the general behavior of the system without external influences. Next is integrating factor method. The integrating factor is defined as this. Multiplying through the equation by this integrating factor helps in simplifying the equation. This method transforms the left side into the derivative of a product, allowing easy integration. Next is finding the particular solution. The particular solution is found by assuming a form based on q of x. Common methods include the method of undetermined coefficients and variation of parameters. Identifying this accurately is crucial for obtaining the complete solution. These are some of examples for the setup correct form of the particular solution. Using this, like this, we can solve all the other questions which is given. Next is method for undetermined coefficients. This method is applicable when q of x is a polynomial, exponential, sine or cosine function. One assumes a form for y of y dash p and determines coefficients by substituting back into the equation. It is an efficient method but may require adjustments for special cases. This is the table for Laplace transform. F of t and f of t is equal to f of s. So a is equal to a by s, t power n, where n is equal to 1 to 3. It is for n factorial by s power n plus 2. E power m is equal to 1 by e power 8 is equal to 1 by s minus a. Sin 80 is a by s square plus s square. s square plus a square. Cos it is s by s square plus a square. Sin h it is a by s square minus a square. Cos h it is sin by s square minus a square. E power at sin bt, b by s minus a whole square plus b square. E power at cos bt, s minus a by s minus a whole square plus b square. T power n e power at n factorial by s minus a of n plus 2 t power n f of t minus 1 whole power n d power n by ds power n whole f of s. E power at f of t is f of s minus a. Y dash t is equals to s y s minus y of o, y of o. Y power a whole t is equals to s square ys minus sy of 0 minus y dash of 0. Variation of parameters. Variation of parameters is a more general method for finding. It involves using the complementary solution to construct a particular solution. This method is versatile and can be applied regardless of the form. Example is given here. We can solve this using integrating factor method. So how to find the integrating factor. Calculate the integrating factor, that is if is equals to this formula. Multiply the entire equation to simplify it. The equation becomes this. Next is solve the simplified equation. The left side can be expressed as derivative of a product. The integrate both sides with respect to this. This leads to the equation. Next is solve for y. Isolate y by dividing. This general equation is this, and this includes both the particular and complementary solutions. Applications of first order non-homogeneous equations. These equations are widely used in modeling real world phenomena such as population dynamics. They also appear in electrical engineering, particularly in circuit analysis. Understanding these equations aids in solving complex systems in various disciplines. Typical second order non-homogeneous ordinary differential equations are this. Next is graphical interpretation. The solution can be visualized graphically to understand their behavior over time. This complementary solution often represents the system's natural response. The particular solution describes the effect of external influence of the system. Next is special cases. Certain forms of this can simplify the solution process. For example, if q of x is constant, the particular solution can be guessed easily. Special cases may allow for closed form solutions that are easier to interpret. Common mistakes. A frequent error is neglecting to find both parts of the solution. Misidentifying the form can lead to incorrect solutions. Failing to check solutions against the original equation can result in overloading mistakes. Conclusion. First order non-homogeneous equations are fundamental in differential equations. Mastering their solution techniques is essential for applied mathematics. Their relevance spans multiple fields, making them a critical topic of study. Next is further reading and resources. Textbooks on differential equations provide in-depth coverage of these topics. Online courses and tutorials can offer additional practice and problem-solving strategies. Research papers and articles can provide real-world applications and advanced concepts. Questions and discussions. Open the floor for questions to clarify any concept discussed. Encourage discussion of practical applications and challenges faced in solving these equations. Invite feedback on the presentation and any for the topics for further exploration. Thank you.